You know that feeling when you stumble onto something really fascinating and you just you want to grasp all the key info like right now?
Hmm.
Well, that's pretty much what we're doing today. We've gone deep into the research on a Jurassic giant, Allosaurus.
Yeah.
So think of this as your fast track to really understanding this, well, iconic predator.
Absolutely. Allosaurus, I mean, it was this huge two-legged dinosaur, right? Lived way back in the late Jurassic. We're talking 155 to maybe 145 million years ago.
And the name itself? Allosaurus.
Different lizard.
Right. Which already tells you something, doesn't it? That even back when they first found it, they knew there was something unusual about its anatomy. Those vertebrae, specifically.
Exactly. They were quite distinctively shaped concave.
And the official description, that goes back to 1877, Othniel Charles Marsh.
That's the one.
Yeah.
He described the first definitive remains. But like you said, the story gets complicated. As you dig into the sources, it's clear the whole process of naming it, figuring out its family tree. Well, it had a lot of twists and turns.
More than a few, it sounds like.
Definitely. For, gosh, more than half of the 20th century, a lot of people actually knew this dinosaur as Antrodemus.
Right, Androdemus.
So, yeah, our mission today is basically to unpack all that history, look at the key features that made Allosaurus such a successful hunter, get into the ongoing debates about, how many species there really were.
And figure out its place in that whole ancient world it lived in.
Precisely. It's a deep dive into a real classic dinosaur. A household name, almost.
Okay, so let's get into that naming drama first, because it sounds like the early days of paleontology were pretty chaotic. We hear about the bone wars a lot. What was that all about, and how did it mess things up for Allosaurus?
Right, the Bone Wars. It was this period, late 19th century, of just intense, almost cutthroat competition between two really big names in paleontology, Othniel Charles Marsh,
Hey, we just mentioned.
yep, and Edward Drinker Cope. Now, this rivalry, it spurred a lot of amazing discoveries, no doubt, but it also led to some, let's say, rushed work, especially when it came to naming things.
Ah, okay. Speed over accuracy sometimes.
Kind of. So for what we now call Allosaurus, the very first fossil related to it was actually described even earlier, 1869, by Joseph Leidy. He first thought it might be a European dinosaur, Poecilopleuron, but then gave it its own genus name, Antrodemus.
Androdemus. So that name actually came first. Why didn't it stick? What happened?
Well, that's the crux of it. Marsh comes along in 77, finds these kind of fragmentary bones in Colorado, Garden Park specifically, and based on those, he names Allosaurus fragilis.
Allosaurus fragilis. Oh.
And the name itself, it's a mix of Greek and Latin. Allos means different or strange.
Hence different lizard.
Exactly. And Soros is lizard. Then fragilis is Latin for fragile, which probably referred to some lightning features, these hollow spaces he saw in the vertebrae.
Okay, but this story didn't stop there, right? More names kept popping up.
Oh yeah, it got even more tangled. Marsh and Cope, in their rush, they kept naming other genera based on, frankly, pretty incomplete fossils too. Things like Creosaurus, Labrasaurus from Marsh, a Pantherius from Cope.
Wow. It really does sound like a free-for-all. Like everyone was finding a different bone and giving it a whole new name.
Pretty much. It was like describing an elephant by just looking at the tail or the trunk or an ear and calling each part a different animal.
So when did people start actually trying to sort this mess out, this dinosaur identity crisis?
Well, Charles W. Gilmore took a big step in 1920. He looked at everything and basically said, look, Antrodemus was named first, so technically it should be the valid name.
Okay, so Antrodemus made a comeback.
It did, for a good long while. But then came James Henry Madsen. His work, especially on that huge haul of Allosaurus fossils from the Cleveland Lloyd Dinosaur Quarry in Utah, that was pivotal.
What did Madsen argue?
He basically argued that the original Antrodemus specimen, the holotype, was just too fragmentary, too poorly preserved, and crucially, they didn't even know its exact original location. You can't really define a whole genus based on something so iffy.
Right, you need a solid benchmark, something reliable to compare other fossils to.
Exactly. You need a good type specimen.
But even Madsen's work wasn't quite the final word. I saw something about a recent ICZN decision.
Ah, yes. Good point. Because that original Allosaurus fragilis holotype described by Marsh was still quite fragmentary, there was lingering ambiguity. So, to nail it down definitively, the International Commission on Zoological Nomenclature, the ICZN, they stepped in just recently, 2023.
And what did they do?
They officially designated a much better, more complete specimen, USNM 4734, as the neotype.
The neotype, so like a new reference standard.
Precisely. It's a replacement type specimen. This action really solidifies the name Allosaurus and gives scientists a much clearer, more robust foundation for identifying and comparing Allosaurus fragilis. It finally cleared up that century-old confusion.
Okay. Dinosaur naming controversy resolved, at least for now. So now that we've waded through that fascinating history, let's get to the really cool stuff. What did this different lizard actually look like? Paint us a picture.
Okay, imagine this massive predator walking tall on two really powerful hind legs. Big skull, but surprisingly lightweight in construction, yet strong, and filled with rows of sharp, serrated teeth. Dozens of them.
How big are we talking?
For the main species, Allosaurus fragilis, the average length is estimated around 8.5 meters, so at what, 28 feet?
That's pretty big.
It is. But some of the largest specimens found might have pushed 9.7 meters, maybe even 10. That's getting close to 32 feet.
Wow.
And actually, some earlier interpretations by Madsen looking at the size range of individual bones suggested they could potentially get even bigger, maybe up to 12 or 13 meters. That's 39 to 43 feet, though most estimates today are a bit more conservative.
Still enormous. And you always picture these big predators with tiny arms, like T-Rex. How did Allosaurus' arms stack up?
Ah, interesting point. They were definitely small compared to those massive legs, maybe only about 35% of the hind limb length in adults. But, and this is key, they were much more substantial than Tyrannosaurus arms.
Really? How so?
Well, Allosaurus had 3 functional fingers on each hand, and each finger ended in a big, sharp, curved claw. The arms themselves were pretty muscular, too. They even had this specialized wrist bone, the semilunate carpal, which probably gave them decent flexibility for grabbing things.
So definitely not just useless little appendages then. They could actually do stuff with them.
Seems likely, yeah. They weren't just along for the ride. Useful for grappling prey, maybe?
Okay, not just for show. Got it.
Hmm?
What else is distinctive? I remember reading something about horns.
Yes. Right above and slightly in front of the eyes, it had a pair of bony crests or horns. These weren't solid bone cords like a triceratops, but extensions of the lacrimal bone.
The tear duct bones.
Basically, yeah. And they were likely covered in a sheath of keratin like our fingernails or bird beaks.
What were they for?
Display, weapons. Good question. Probably display, primarily. Maybe for showing off to mates or intimidating rivals. They varied a lot in size and shape between individuals. It's possible they were used in pushing contests with other Allosaurus, but display seems more likely. There were also these lower paired ridges along the snout on the nasal bones that led up into those horns.
Huh. And the teeth. You mentioned sharp and serrated.
Oh yeah, classic theropod teeth, designed for slicing meat. And like sharks, they were constantly replacing them. Lose one, break one, another one grows in, ready for action.
Always sharp. And what about the skull itself? You said lightweight but strong.
Right. It had a lot of openings, called fenestrae, which reduced weight, but the structure was quite rigid overall. Interestingly, it also had flexible joints within the skull and between the lower jaws.
Flexible. Yeah.
Why? Probably allowed it to swallow larger chunks of food and maybe withstand the stresses of struggling prey. It suggests they could open their mouths really wide, a wide gape.
Okay. Horns, killer teeth, powerful legs, useful arms. Quite the package. Now, you mentioned Allosaurus fragilis, but our source material listed quite a few species names. Is Allosaurus really that diverse a group, or is a lot of that still up for debate?
That's a great question, and yes, it's definitely an active area of research and debate. Over the years, about 7 species have been formally named, but until very recently, say before 2020 and the naming of A. annex, the general consensus among most paleontologists recognized maybe 3 as potentially valid.
Okay, which 3?
The type species, A. fragilis, which we've talked about. Then there's A. europaeus, which was found in Portugal.
Europe. So Allosaurus wasn't just North American.
Apparently not, although the status of A. europaeus has been debated. Some studies question if it was really distinct enough from the American species, but actually a very recent study, I think from 2025 mentioned in the source, seems to confirm it is valid and interestingly suggests it might be more closely related to the other commonly accepted North American species, A. jimetseni, than it is to A. fragilis.
Okay, wait. A. jimetseni. That's the third one.
That's the third one, yes. And then there's the complication of some really nice fossils from Portugal, the Andre specimens. They've been bounced around a bit taxonomically assigned to A. fragilis, just Allosaurus sba europaeus, and now often called Allosaurus ef europaeus, meaning compare to europaeus. So it's still a bit fuzzy.
So even within the group, there might have been distinct European and North American types, possibly even multiple North American ones.
Yeah.
What are the key differences between Fragilis and this Jimitseni?
Right, so A. fragilis is kind of the classic one, found pretty much throughout the Morrison Formation in the western USA, Jimitseni, named, by the way, after James Madsen, the paleontologist who did so much work at Cleveland Lloyd.
Ah, makes sense.
Yeah. It was initially thought to be maybe older from lower down in the Morrison layers, specifically the saltwash member, but newer studies suggest they actually lived at the same time they were coeval, but perhaps geographically separated for the most part. A. fragilis seems more common in the southern parts of the Morrison, while Jimitseni is found more often up north.
Are there physical differences?
Yes, one of the key ones paleontologists use is the shape of the jugal bone that's part of the cheek. In A. jimitseni, the bottom edge of that bone is noticeably straight, whereas it's more curved in A. fragilis.
Interesting, these subtle differences. And then there's the newest one, ANX, named in 2024.
Correct, Allosaurus annex. This one's based on fossils that were actually previously assigned to a different, potentially dubious, giant theropod genus called Saurophaganax.
Oh, Phaganax. Sounds impressive.
It does. And the researchers who named A. annex identified some specific features they say distinguish it from other Allosaurus. Things like lacking rough texturing on a skull bone called the postorbital, and having distinctly hourglass-shaped vertebral bodies, the centra, in its back vertebrae, which also had lots of air sacs or pneumatic openings.
And the name? Annex.
It's Greek for king or lord, probably a nod to that earlier Saurophaganax identity, which itself means lizard-eating master.
Huh. Okay, so the Allosaurus family tree is definitely still a work in progress. What about those other names we saw floating around? Creosaurus, Apanturias, Labrosaurus. Are they just old names for Allosaurus now?
Pretty much, yeah. Creosaurus is widely seen as just a junior synonym, an older name for the same thing. Epanturias and Labrosaurus are maybe a little more debated. Their status needs more study, but they're also generally considered synonyms of Allosaurus.
Labrosaurus had some weird jaw thing, right?
Exactly. Labrosaurus ferox was named based on a lower jaw that looked really odd. But now most scientists think that weird shape was probably due to an injury or disease the animal had when it was alive, pathology, basically. Not a reliable feature to define a whole new genus.
So not a different species, just an unlucky individual.
Likely, yes. And that older idea, you might see it in older books, that there were two main species in the Morrison A. fragilis and a supposedly more robust one called A. atrox that's also mostly fallen out of favor. The differences are now generally thought to be just individual variation within A. fragilis or perhaps representing A. jimitseni.
Got it. And there were some other names too, just typos or invalid ones.
Yeah, things like Madsinius, Wyoming graptor, white-eye, those are generally considered nomina nuda, meaning they weren't properly described or they were based on misidentified material. It just shows how science corrects itself over time as we get more fossils and better analysis.
Absolutely fascinating. It's not just digging up bones. It's this whole detective story of interpretation that keeps evolving. Yeah. Okay, so we've got a clearer picture of the Allosaurus species situation. Now let's really get into how this animal lived. What do we know about its life cycle? How fast did it grow?
We can actually learn a lot from looking inside the bones at their microscopic structure, that's bone histology. Based on growth rings, kind of like tree rings, estimates suggest Allosaurus lived maybe 22 to 28 years.
Similar to T-Rex then.
Yeah, in that ballpark. And their fastest growth spurt seems to have hit around age 15. During that time, they might have been packing on something like 150 kilograms a year. That's over 300 pounds.
Wow, rapid growth.
Definitely. And there was this really interesting find, though it's still debated, possible medullary bone in one specimen.
Medullary bone, what's that?
It's a type of bone tissue that female birds produce when they're laying eggs. It's a calcium reserve for the eggshells. If this identification holds up, it could mean that particular Allosaurus was a reproductively mature female.
That would be incredible. Direct evidence of sex in a dinosaur fossil.
It would be. But some researchers are cautious, suggesting it could potentially be some kind of bone disease or pathology instead. So the jury's still out on that one.
Okay, intriguing but not confirmed. What about baby Allosaurus versus adults? Were they just mini versions or different?
There's a great juvenile specimen that tells us a lot. Its legs, especially the lower parts, the shin bone and foot, were proportionally much longer compared to adult Allosaurus.
Longer legs, so faster.
That's the thinking. It suggests the youngsters might have been quicker, more agile. Maybe they hunted smaller, faster prey than the big adults did. As they grew, their thigh bones got much thicker and wider, suggesting their muscles changed, probably shifting towards more power for tackling larger animals, maybe using ambush tactics more.
So, a lifestyle shift as they grew up.
Seems plausible. Interestingly, while the leg bones changed shape quite a bit during growth, the skull bones seem to have grown more isometrically, meaning they just got bigger without changing proportions dramatically.
Okay, from speedy juniors to powerhouse adults. Makes sense. Now, the big question, what did they eat? What's the actual proof?
We have some pretty solid direct evidence. Puncture wounds found in Stegosaurus tail vertebrae that are healed over, showing the Stegosaurus survived the attack, and the spacing perfectly matches Allosaurus teeth.
Wow, like a fossilized crime scene.
Kind of, and there's a Stegosaurus neck plate with a big U-shaped bite mark taken out of it that also perfectly matches the shape of an Allosaurus's snout.
Ouch.
Huh.
So definitely hunting stegosaurs. What about the giant sauropods?
Almost certainly. They were likely a major food source, maybe targeting the juveniles more often, as taking down a full-grown Apatosaurus or Diplodocus would have been incredibly dangerous. But we find lots of Allosaurus tooth marks on sauropod bones, and also shed Allosaurus teeth mixed in with sauropod skeletons. That points to both predation and scavenging.
Right, eating them after they died too.
Hmm.
So Allosaurus was clearly a capable hunter, but there's always been this debate about how it hunted, right? Was it like T-Rex, crushing bone, or something else?
Yeah, that's a classic debate. Robert Baker, a well-known paleontologist, famously compared Allosaurus to saber-toothed cats. He noted things like strong neck muscles and a wide gape and proposed this slashing attack.
Slashing, how would that work?
The idea was that maybe Allosaurus didn't have the immense bite force to crush bone like Tyrannosaurus, but instead used its upper jaw, lined with those serrated teeth like a saw or a hatchet. It would slam its head down or sideways into large prey, tearing out big chunks of flesh and causing massive bleeding.
Yikes, like a giant steak knife.
Sort of. And some biomechanical studies using finite element analysis like engineers use to test bridges.
On a dinosaur skull. Cool.
Yeah. Those studies suggested the skull was very strong, could take a lot of impact stress, but the actual bite force wasn't relatively as high as you might expect for its size, certainly less than T-Rex. This seemed to support that hatchet head idea, but it's definitely still debated. Not everyone agrees with that interpretation.
So maybe not a bone crusher, but a flesh tearer. What about that other idea mentioned, the flesh grazer on living sauropods? That sounds grim.
It is a pretty dramatic image. The hypothesis is that maybe Allosaurus could take large bites out of the flanks of huge living sauropods, animals too big to kill outright easily. It wouldn't kill the sauropod immediately, but it would provide a meal and potentially weaken the giant over time, kind of like, well, grazing on flesh.
Wow. Okay. Are there other ideas about how it hunted smaller prey?
Yeah, another thought, especially for things like ornithopods, medium-sized plant eaters, is that Allosaurus might have used those surprisingly strong arms and claws to grab and hold the prey.
Right, the arms weren't useless.
Exactly. Grapple the prey, hold it steady, and then deliver a killing bite, perhaps to the throat, targeting the trachea.
Makes sense. You mentioned the wide gape earlier. How wide are we talking?
Biomechanical studies suggest it could open its mouth incredibly wide, potentially even wider than Tyrannosaurus or another theropod called Erlikosaurus. And while the absolute bite force might not have been T-Rex level, the jaw muscles were still very strong.
So maybe it traded some crushing power for the ability to open really wide.
That's one interpretation. And there's another interesting anatomical detail. The way a key neck muscle attached low down on the back of the skull. This would have allowed for really rapid, powerful up and down movements of the head.
Like a head-banging motion.
Sort of, yeah. Think powerful vertical strikes. This supports the slashing hypothesis, but could also be useful for processing carcasses, pulling flesh off bone, similar to how falcons feed today.
Okay, so multiple lines of evidence pointing towards different possibilities.
Yeah.
What about its senses? Was it relying on sight, smell?
Looking at the skull, the eye sockets suggest it had somewhat limited binocular vision, where the fields of view from both eyes overlap. Maybe about 20 degrees, similar to a modern crocodile.
Is that enough to hunt effectively?
Probably good enough for judging distance to prey reasonably well. Maybe not superb depth perception, but functional.
Yeah.
Its inner ear structure suggests it was better at hearing lower frequency sounds. Maybe not great with high-pitched noises, but its olfactory bulbs, the part of the brain for smell, were quite large. This indicates it likely had a very good sense of smell.
So maybe sniffing out prey or finding carcasses?
Both, most likely. A good sense of smell is invaluable for a predator and scavenger.
And speaking of scavenging, the sources seem to really emphasize that for Allosaurus.
Yes, absolutely. When paleontologists examine sauropod bones from the Morrison, they find Allosaurus bite marks everywhere, on bones showing different stages of decomposition. This is strong evidence that scavenging was a significant part of its lifestyle.
So not just a noble hunter, but happy to eat leftovers too.
Definitely. A huge dead sauropod is a massive amount of food. Why pass that up? It's even been suggested that individuals with injuries that made hunting difficult, like the famous big owl specimen with all its pathologies,
Right, the one with lots of injury.
might have survived primarily by scavenging. And the fact that we find so many healed injuries in Allosaurus fossils, perhaps more than in some other theropods, might suggest they were tough animals that frequently survived risky encounters, whether hunting or scavenging or fighting each other.
Fascinating. An opportunist, basically,
Mm-hmm.
taking whatever meal it could get. Okay, now the question that always comes up with big predators. Did Allosaurus hunt in packs?
Ah, the pack hunting debate. It's been a popular idea since the 70s, especially for tackling those giant sauropods. You see it in movies and books all the time.
Baker suggested it, right? Even parental care.
He did. He pointed to sites with shed teeth and chewed bones as possible layers where adults might have brought food back. But the hard evidence for truly coordinated pack hunting in large theropods like Allosaurus is actually pretty thin.
Really? So maybe not wolf-like packs?
Probably not. Many paleontologists now lean towards the idea that interactions between Allosaurus were more likely competitive, even aggressive. Think disputes over territory, or especially over carcasses.
Like lions squabbling over kill.
More like that, or perhaps even like Komodo dragons converging on a carcass. Those sites with lots of Allosaurus skeletons together, like Cleveland Lloyd.
Yeah, what's the thinking there now?
Instead of a pack that died together, it might represent a predator trap scenario. Maybe one animal gets stuck in mud, its struggles attract others, hoping for an easy meal, they get stuck too, maybe fight each other. It becomes a deadly pileup over time.
And you mentioned potential cannibalism?
Yes, there's evidence for that. Allosaurus tooth marks found on Allosaurus bones at some of these sites. And injuries found on skulls and belly ribs also strongly suggest they fought with each other, sometimes lethally.
So maybe less teamwork and more every dino for itself at a feeding frenzy.
That seems to be a more likely scenario based on current evidence, though some argue the sheer number of injuries suggests they lived in groups where such interactions were common. Gregariousness doesn't automatically mean cooperative hunting.
Right. Okay, what about their brains? Were they smart for a dinosaur?
Well, smart is tricky to define, but looking at endocasts molds of the inside of the brain case, the overall brain structure of Allosaurus seems more similar to modern crocodilians than to birds.
Crocodiles aren't exactly known for complex thought.
Right. Doesn't mean they were stupid, just differently adapted. Their balance organs suggest they usually held their heads fairly level, horizontally. And as we said, the inner ear was more croc-like, tuned for lower frequencies. Olfactory bulbs were good, but not exceptionally huge relative to body size.
Okay. And before we put Allosaurus in its environment, tell us a bit more about those injuries and diseases. Paleopathology, right?
Yes, paleopathology. It tells us a lot about their rough lives. We see lots of stress fractures, especially in the arms and feet. Also tendon avulsions, where tendons rip bits of bone off.
Ouch. What does that suggest?
It strongly suggests they were physically grappling with large, struggling prey, holding on, wrestling. That puts immense stress on bones and tendons. And interestingly, Allosaurus seems to have significantly more of these types of injuries than some other big theropods like Tyrannosaurus.
Really? Why might that be? Different hunting style.
Possibly. Maybe their hunting involved more direct, prolonged physical contact and struggle. We also find healed breaks, bone infections like osteomyelitis, weird bony growths, signs of arthritis in the joints.
Arthritis. Dinosaurs got arthritis.
Apparently so. Even a type of spinal arthritis called spondyloarthropathy. The first known case in a theropod was found in an Allosaurus. Again, specimens like Big Al are just riddled with evidence of past trauma and disease. They were clearly resilient animals.
Wow, it really paints a picture of a tough existence. Okay, so we have this big, powerful, potentially scrappy, opportunistic predator riddled with old injuries. Where did it fit into the bigger picture? The late Jurassic world.
It was absolutely central. In the Morrison Formation environment of Western North America, Allosaurus was the most common large theropod. We're talking 75% of all large predatory dinosaur specimens found there belong to Allosaurus.
70 to 75%. That's dominant.
Hugely dominant. It puts it firmly at the top of the food chain in that ecosystem.
And what was that ecosystem like, the Morrison?
It was a vast area characterized by distinct wet and dry seasons. You'd have had big, flat floodplains, rivers lined with forests of conifers, ginkgos, tree ferns, and then more open areas, kind of like fern savannas.
And who else lived there? What were its neighbors?
Oh, it was a spectacular dinosaur fauna. You had other theropods, though less common, like Ceratosaurus, Ornitholestes, the big Torbosaurus, then the sauropods, the real giants, Apatosaurus, Brontosaurus, Camarasaurus, Diplodocus, Brachiosaurus, Stegosaurus. The list goes on.
The classic Jurassic lineup.
Exactly. And lots of smaller plant eaters too, like Camptosaurus and Dryosaurus. But interestingly, Allosaurus fossils are very often found in the same spots as Patasaurus, Camarasaurus, Diplodocus, and Stegosaurus.
Suggesting those were common neighbors and probably common prey items.
Very likely. And remember, similar dinosaurs, including Allosaurus, Ceratosaurus, and Torvosaurus, are also found in Portugal from the same time period. The environments were similar, though Portugal had more of a coastal marine influence.
So even with other big predators like Ceratosaurus and Torvosaurus around, Allosaurus was king. How did they coexist? Did they hunt different things or live in slightly different places?
That's the idea in niche partitioning. It's thought they probably specialized somewhat to reduce direct competition. Maybe Ceratosaurus and Torvosaurus, based on where their fossils are found and some anatomical differences, preferred areas closer to water, maybe more forested habitats.
Well, Allosaurus took the open plains.
Potentially. Allosaurus seems better adapted for drier, more open floodplain environments. And they do have anatomical differences. Ceratosaurus, for instance, had a taller, narrower skull and broader, more blade-like teeth than Allosaurus, maybe suggesting different prey or feeding techniques.
So they carved up the environment in the menu a bit?
Probably. We even have possible evidence of Allosaurus itself being scavenged by one of the other's bite marks on an Allosaurus pubic bone that seemed to match the teeth of Ceratosaurus or Torvosaurus.
Wow. Turnabout is fair play in the Jurassic.
It seems so. And the sheer number of bite marks found on herbivore bones in the Morrison, mostly attributed to Allosaurus and Ceratosaurus, suggests they were very thoroughly utilizing the available food, maybe especially during tough dry seasons. Or it could just be a bias in what gets fossilized and found.
A complex, dynamic world. It's incredible how much detail we can piece together.
It really is. Allosaurus wasn't just some monster, it was a key part of a functioning ecosystem millions of years ago, and its fossils are still teaching us so much.
Well, this has been an absolutely fantastic deep dive into Allosaurus. We've covered so much ground from that tangled naming history.
The Bone Wars chaos.
Right. To its really impressive physical build. Those debates about how it hunted the slashing versus crushing.
The species confusion, which is still being sorted out.
And its clear dominance in that late Jurassic Morrison ecosystem.
Yeah, we touched on the evidence for slashing attacks, the wide gape, the potential for scavenging, the arguments about pack hunting versus maybe more aggressive solo interactions.
And all those injuries. The paleopathology really brings their tough lives into focus.
It really does. The healed fractures, infections, arthritis, it tells a story.
And it really makes you wonder, doesn't it?
Yeah.
When you weigh all that evidence, the predation, the scavenging, the potential for cooperation, but also definite signs of aggression, maybe even cannibalism. What does Allosaurus really tell us about life at the top? About the pressures and challenges of being the apex predator in that world?
And what does that high rate of injury actually signify? Was it just the cost of doing business as a top predator back then? The risks involved in tackling giant prey or maybe fighting rivals?
It's definitely a lot to chew on. Hopefully this has sparked your curiosity, too, to maybe explore even more about the absolutely captivating world of late Jurassic paleontology.